Picture two different ways of having a conversation. The first way, you say something, wait for the other person to confirm they heard you, then say the next thing. If they didn't hear you clearly, you repeat it. Nothing moves forward until both sides are in sync. It's slow, but nothing gets missed. At the end of the conversation, both sides have a complete, accurate, shared understanding of everything that was said. The second way, you just talk, continuously. You don't wait for confirmation. You don't repeat yourself. If a word gets lost in background noise, it's gone. You've already moved on. The conversation flows fast, but the listener might miss things, and neither side will necessarily know exactly what was and wasn't received. These aren't just communication styles. They're a precise description of the two fundamental delivery models that the internet is built on. One is called TCP, the other is called UDP, and the choice between them is one of the most consequential design decisions in any networked application. Let's start with TCP, because it's the one most of your internet activity runs on without you knowing it. TCP stands for Transmission Control Protocol. The name is revealing. It's a protocol specifically designed to maintain control over a transmission, to ensure it goes correctly, to detect when it doesn't, and fix it. Here's the core mechanism. When you send data over TCP, the receiving side sends back a small acknowledgement message for everything it receives, essentially saying, "Got it." The sending side keeps track of what it's sent and what it's received acknowledgements for. If an acknowledgement doesn't come back within a certain time, the sender assumes the data was lost and retransmits it. This cycle, send, acknowledge, detect loss, retransmit, continues until every single byte has been confirmed received. Additionally, TCP numbers every byte it sends. The receiving side uses these sequence numbers to reassemble data in the correct order, even if packets arrive out of sequence. A packet that arrives early gets held in a buffer until the missing earlier packets arrive and fill the gap. The result is a delivery guarantee that's remarkably strong. Everything sent arrives in order without duplicates or the connection fails trying. TCP doesn't give up silently. If data is lost, it retransmits. If it loses the connection entirely, it tells you. What it never does is deliver partial, corrupted, or out-of-order data to your application without your knowledge. This guarantee is why TCP is used for almost everything where correctness matters. Web pages, file downloads, emails, database queries. In every case, the data has to be complete and accurate. A web page with missing HTML is broken. A downloaded file with missing bytes is corrupted. An email with missing paragraphs is wrong. TCP's guarantees are what make these things work reliably, but those guarantees have a cost. And to see the cost, you have to think about what happens when something goes wrong on the network. Suppose you're downloading a file over TCP, and a packet gets lost, dropped by a congested router somewhere along the path. TCP detects the loss, waits a moment, retransmits the missing packet. The download pauses imperceptibly, the missing piece arrives, and everything continues. The application never sees a gap. The file arrives complete. Now suppose you're on a live video call over TCP and a packet gets lost. TCP detects the loss and retransmits. But here's the problem. The retransmission takes time. While waiting for the missing packet, TCP holds back everything that arrived after it, because it has to deliver things in order. Your video freezes. Your audio cuts out. The call hangs while TCP waits for data that was already stale the moment it was lost. When the retransmission finally arrives, maybe 100 milliseconds later, maybe 300, it represents a moment in the conversation that has already passed. Delivering it perfectly, in order, is useless. It needed to arrive then, not now. TCP's guarantee that everything arrives correctly and in order is not just unhelpful for live video. It actively makes things worse, because it introduces delay and stalling in exchange for correctness nobody needs. This is the fundamental problem TCP solves poorly for real-time applications. The guarantee costs time, and time for real-time data is the one thing you cannot recover. This is where UDP comes in. UDP stands for User Dadgram Protocol. If TCP is the careful, confirmation-seeking conversation, UDP is the continuous broadcast. You send packets. They either arrive or they don't. You never find out. The receiver gets whatever shows up, in whatever order it shows up, with no acknowledgement, no retransmission, no reordering. That sounds on its face like a worse system, and for many use cases, it is. If you tried to download a file over UDP, you'd get random bytes missing, data out of order, no indication of what arrived and what didn't. It would be unusable. But for real-time applications, live video, voice calls, online gaming, live streaming, UDP is not just acceptable, it's the right choice. Think about what a video call actually needs. It needs data to arrive fast. It needs continuous flow, a new frame every 33 milliseconds, audio samples hundreds of times per second. What it doesn't need is perfection. A video frame that arrives with a few pixels wrong is imperceptibly degraded. A video frame that arrives 300 milliseconds late because TCP was waiting for a retransmission causes the call to freeze and stutter visibly. With UDP, a lost packet is simply a brief glitch, a blurry moment, a slight audio artifact. The application moves on immediately to the next frame, the next audio sample. No waiting, no stalling. The call stays fluid, even at the cost of occasional imperfection. This trade-off, accepting imperfect delivery in exchange for continuous, low-latency flow, is exactly what real-time applications need, and UDP provides it by simply not making the guarantees TCP makes. It's not a broken version of TCP. It's a deliberately minimal protocol designed for applications where the overhead of TCP's guarantees does more harm than good. Here's a useful way to map this to applications you use every day. Your browser loading a web page, TCP. Every byte of HTML, CSS, JavaScript, and images has to arrive correctly for the page to render properly. No tolerance for loss. Sending an email, TCP. You want the complete message to arrive exactly as you wrote it. Downloading a software update, TCP. A corrupted update is worse than no update. A live video call, UDP. Speed and continuity matter more than perfection. Online gaming, UDP. A game running at 60 frames per second cannot afford to stall waiting for retransmissions. A position update that arrives late is worse than one that never arrives. Live radio or television streaming, UDP. A brief audio glitch is tolerable, a buffering pause is not. DNS lookups, UDP. Short, fast requests and responses where the overhead of establishing a TCP connection would take longer than the lookup itself. If a DNS query is lost, the application just sends another one. The pattern is consistent. Correctness over speed, TCP. Speed over correctness, UDP. But the story doesn't quite end there, because the real world is messier than a clean binary choice. Many modern applications need something in between, mostly fast, but with some reliability guarantees. A messaging app needs messages to arrive in order and without loss. But it also doesn't want to stall if a packet is briefly delayed. A file transfer over a video game's infrastructure needs reliability, but also needs to coexist with the real-time game data without adding latency. These applications often build their own reliability mechanisms on top of UDP. They implement selective acknowledgements, not for every packet, but for important ones. They implement their own ordering, their own retransmission logic, tuned specifically to what they need rather than what TCP provides generically. They get the control of building their own delivery rules without the overhead of TCP's full guarantee stack. This is a significant trend in modern networking. QUIC, the protocol underlying HTTP/3, the latest version of the web's core protocol, is built on UDP rather than TCP, with its own reliability and ordering mechanisms implemented above the transport layer. The developers of QUIC decided that TCP's guarantees, while correct, came with constraints, particularly around connection establishment time and handling of packet loss, that could be improved by building fresh on top of UDP. So the choice isn't always strictly TCP or UDP as is. It's really a choice about what delivery properties an application needs and whether TCP's specific implementation of reliable delivery is the right fit, or whether building something more tailored on top of UDP makes more sense. TCP and UDP are not a good option and a bad option. They're two honest answers to the same question. Given that the network is imperfect, that packets get lost, delayed and delivered out of order, what should we do about it? TCP says, fix it. Detect every problem, correct every error, deliver everything perfectly regardless of how long it takes. UDP says, accept it, move fast, tolerate imperfection, let the application decide whether what arrived is good enough. Both answers are right, in the right context. The art is knowing which context you're in and choosing accordingly.